Hi, this is David Rind, and I'm pleased to be able to introduce our speakers today. The first speaker is Tony Del Genio, who's a senior research scientist at NASA's Goddard Institute for Space Studies. Tony has developed cumulus and stratiform cloud parameterizations for the GISS climate models for a number of decades now. His research focuses on climate feedbacks, the hydrologic cycle, interactions with the general circulation, and comparative dynamics of planetary atmospheres, including exoplanets. Clouds are a very, not pun withstanding, cloudy subject. And I've heard many cloud talks over the years, and Tony by far presents the clearest, most coherent presentation of this somewhat oblique subject. So we're really very fortunate to have Tony available to give this talk. Tony, thanks very much.
Good afternoon. Thank you for listening into this today. I'm happy to be here and speaking to you about the role of clouds in climate. I'm Tony Del Genio, and we're going to start by talking about how clouds appear in the sky. Clouds form when little blobs of air, meteorologists call them parcels, but think of it as a little blob of air, an air that contains moisture, humid air in particular. When those little blobs of air rise to higher altitude and therefore lower pressure, they expand and they cool, and they do work against the environment that surrounds them, and they have to use up energy to do work. And once they do that, that means they have to cool. And when they cool, that means that the water vapor, the gaseous phase of water that they contain, is more likely to become saturated, that is, to reach the maximum value at which it can exist before it begins to condense from a vapor into liquid. We call that the saturation point, or in everyday terms, we would call that 100% relative humidity. When that happens, the air begins to condense water vapor out of it and form cloud droplets. And so that means when you look at a satellite image of the Earth, like the one at the top of this slide, then the places where you see clouds are usually places where air is rising. And so clouds act as tracers or dye markers, if you will, of the general circulation of the atmosphere, especially the troposphere. Okay. There are two fundamentally different types of clouds, and they play different roles in the climate. And that's going to be something that you hear over and over again during this talk, how different types of clouds play different roles in weather and climate. So the one way to divide up the clouds is into convective and stratiform clouds. Convective clouds are formed when air rises because it becomes unstable. It becomes warmer and less dense than the air surrounding it, sort of like a hot air balloon. And that tends to happen when the air that rises is humid, and when the lapse rate, that is the rate at which temperature decreases upward, exceeds the rate at which the temperature of the rising air decreases upward, which is called the moist adiabatic lapse rate. When that happens, the rising air becomes warmer and buoyant relative to its surroundings, and therefore it rises of its own accord after that. You don't have to give it any more than that initial push. That's a convective cloud. But a lot of clouds do not form under those circumstances, so you can also form clouds when vertical motion happens in other ways, such as when there is a cold air mass sitting over a particular part of the Earth's surface, and warm air masses move up toward that cold air surface, and they're less dense than the cold surface and just get pushed up and over the cold surface. You can also get clouds when the air right next to the Earth's surface, which is called the boundary layer, becomes turbulent. People understand turbulence when they're flying an airplane through turbulent skies. When you have that kind of turbulence, little blobs of air are moving up and down all over the place, and that can make clouds too. We call those clouds stratiform clouds. Okay. A little bit more about convective clouds. Convective clouds come in two basic flavors, shallow and deep. Shallow cumulus clouds, or what we call fair weather cumulus clouds, are the types of clouds that you'll see on a beautiful summer day, maybe about 1 o'clock in the afternoon, when you might see these little cotton ball things hanging out in the sky and just passing overhead. They're, very pretty looking. They rarely make rain, but when they do make rain, it's usually small amounts of rain for a brief amount of time. And nonetheless, even though they're very modest looking, they play a very important role in climate, because the water vapor that is in the atmosphere, the humidity of the atmosphere, comes from water that is evaporated from the ocean surface into the air. These shallow fair weather cumulus clouds take that evaporated water from the ocean surface and lift it up to higher altitudes, where it can get caught up in the prevailing winds and moved all over the globe as part of the general circulation. The other thing about these clouds is that there are enough of them in the sky that they make the Earth significantly brighter than it would be without them. And so they have a radiative impact on our climate. That is, they change the amount of sunlight that is reflected by the Earth. The other type of convective cloud, deep cumulonimbus clouds, are what we normally think of as the clouds that storms, torrential rainstorms, thunderstorms, things like that. They are very deep clouds that go from near the surface of the Earth all the way up to the tropopause. They're responsible for most of the Earth's precipitation. They have a net effect of making the air warmer and drier than it was before they came by, because they squeeze water out of the atmosphere and turn water vapor into liquid water. And they're the source of about half of the cirrus clouds that we see at higher altitudes in the atmosphere, and I'll be talking about those in a minute. Okay, stratiform clouds come also in several different flavors. The low and middle altitude clouds are in one class, and the high clouds are, cirrus clouds are in another class. The low and middle clouds tend to mostly be made of liquid droplets, but in some places, they can be made of either ice, for example, up in the Arctic, or in what we call mixed phase clouds, clouds that have some liquid and some ice in them. They too usually produce little precipitation or no precipitation. We're talking about clouds that are normally referred to as stratus clouds or stratocumulus clouds, but some of them are thicker and produce significant precipitation. We call those nimbostratus clouds. So if you're on the east coast of the United States today, you've probably encountered some nimbostratus clouds that have been putting a lot of rain down on the ground. Low and middle clouds can cover large areas, and they're important because they reflect a lot of sunlight. They don't have much of a greenhouse effect the way some other clouds do, because they're at a low level and they do not result in the Earth emitting any less heat to space than they would if the clouds were not there. We call that they're lying beneath the clear sky emission level. High clouds are almost always made just of ice. They come in thin flavors and thick flavors. The optically thin flavors, which we call cirrus clouds, reflect very little sunlight. They're clouds that you would think of as being translucent. You can see the sun through them. And the other kind that are thicker, we call anvil clouds or anvil cirrus clouds. Sometimes they're a part of the category called cirrostratus, and those reflect lots of sunlight. High clouds almost always make snow, which might be surprising to some people because the snow that they make usually doesn't make it to the ground as snow. Either the snow that they make dissipates on the way downward in what we call virgo or mare's tail, so that you don't see anything happening at the ground, or they reach the melting level of the atmosphere and turn from ice into liquid water and make rain at the ground. And these high clouds, unlike the low and middle clouds, are very important for the greenhouse effect because they live at high altitudes, which is above the level at which the atmosphere would otherwise radiate heat to space, and they cause the atmosphere to radiate less heat to space than the atmosphere would otherwise. So imagine that you take a trip, and if we look at the satellite image on the left of the Earth, we see two itineraries that you might take, the one on the top in yellow and the one on the bottom in red. Let's think about the trip that we would take for the itinerary in yellow. You start out in the middle of the Pacific Ocean, sort of due west of San Francisco, and you start heading toward the northeast. and you gradually move up to higher latitudes, past Seattle, up into Canada, until you're already up into the Arctic and maybe at the North Pole. The diagram B on the left shows you a cross-section of what types of clouds you encounter along the way. At the high latitudes, storms like the ones we're having today on the East Coast, the storms that usually you encounter in the United States when low pressure centers move over your location with warm fronts and cold fronts, those are the types of storms we're thinking about, in which warm, humid air rides up and over a cold air mass. You pass those clouds, and if you go all the way into the Arctic, you will find at lower levels stratus clouds that can be made of ice or a combination of liquid and ice. Often they're a combination of liquid and ice. The other trip you can take is the one indicated by the red curve, where you start out in the middle of the Pacific Ocean near the equator, and again head northeast until you hit the coast of Southern California. And when you take that trip, you're encountering the tropical general circulation, in which air rises near the equator all the way up to the tropopause, and then it drifts poleward, and then it sinks back near the surface in the subtropics, that is, latitudes like where Hawaii is, for example. And that circulation, which is called the Hadley cell, another component of that circulation that goes from the West Pacific across to the East Pacific near the equator, is called the Walker circulation. And when you go through that circulation, you initially encounter big, thick, heavily raining cumulonimbus clouds, and then eventually, as you go poleward, you encounter shallower cumulus clouds, and then finally stratocumulus clouds once you're near the coast of Southern California. And so this is where the different types of clouds that I've been speaking about tend to occur in nature. You can objectively identify these different cloud types from satellite images just by measuring the amount of sunlight that they reflect, and scientists call that, a measure of that, the optical thickness. And you can also observe from space how much heat or infrared radiation they prevent from being emitted to space. And that depends on how high they are. And when you do that, then you find that for the tropics, you can really classify 6 different types of clouds, 3 that would occur under what meteorologists would call disturbed conditions, meaning conditions that are prone to making rainstorms, and 3 types that are under suppressed conditions. Those are conditions in which rain and deep development of clouds is suppressed by the state of the atmosphere. And those 3 types of clouds in the disturbed conditions are the organized deep convective clouds, the cirrostratus and anvil clouds, and isolated deep mid-level and shallow convective clouds. And then the suppressed clouds are the cirrus clouds, the shallow cumulus clouds, and the stratocumulus clouds. Okay, going on to the next slide. Looking at the mid-latitudes, and this is obviously the part of the world that most of us are familiar with, on the upper left there, we have sort of a composite diagram of what the flow of air looks like in the vicinity of a surface low pressure center. And in this part of the world, there's a tendency for the winds to blow from west to east. And as you near a low pressure center, the air tends to move in a somewhat counterclockwise direction in the northern hemisphere, opposite in the southern hemisphere. And that counterclockwise flow takes the air around the low pressure center and then up to higher latitudes east of that low pressure center. And if you look at the lower left diagram, you can see what the typical pattern of vertical velocity, that's up and down motions, are. So the places that are blue are places where the air rises. The places that are red are places where the air sinks. The places where the air rises are much more prone to make clouds, and in particular thick clouds that may eventually rain. And so if you took a ride through that blue region from south to north and looked at the cross-section of clouds that occurred in that region, you get the picture that we see in the upper right-hand corner, which is actually satellite data from a radar that sees through the clouds and a LiDAR that partially sees through the clouds. And you can see that as you go from the south to the north, once you encounter the surface warm front, all of a sudden things get much cloudier. The clouds get thicker the farther you go north of the surface warm front. And you can see that the cloud pattern you get is sort of tilted because this air is riding up and over a cold air mass. Okay, and so you'll get different cloud types depending on where you are relative to that surface warm front. And given the direction in which these things move, usually the first thing that you see are mid-level altocumulus and altostratic cumulus clouds that occur before the front passes. And then as the front gets closer and closer, the cloud bases descend and you get these big, thick nimbostratus clouds. And those are the things that tend to produce rain and snow like we're having today. Okay, moving up to the Arctic. Polar clouds often occur over the sea ice or snow. They are the hardest clouds to detect in satellite images because sea ice and snow are bright at the wavelengths our eyes are sensitive to, the visible part of the spectrum, and clouds are also bright. And so you stick a bright cloud over a bright surface, it's sometimes hard to tell that the cloud is there. If you look at that image, you can kind of tell that the clouds are in the sort of upper and left part of the diagram and the sea ice is in the lower right part of the diagram, but it's not always that easy to tell the clouds and the sea ice apart. But if you're standing at the surface beneath the clouds, it's very easy actually to detect them even if you're not there to see them, because it turns out that in the presence of clouds, there's a lot of heat radiation, infrared radiation that is emitted downward to the surface that does not occur when the clouds are not there. And we use that then to track Arctic clouds and to see how the presence or absence of Arctic clouds varies according to the weather, according to the weather systems that create those clouds. And what we find is that when the Arctic is under high pressure, usually the skies are clear in the Arctic, or at best they have very thin ice clouds that are almost transparent. When that happens, there's nothing to prevent the sea ice surface from radiating lots of heat up into the atmosphere and out to space. And so the sea ice cools, and that helps maintain the sea ice. If instead you have a low pressure system over the Arctic, that's when thicker liquid water clouds form, and those things are thick enough that they do not allow heat radiated upward to escape. Instead, they produce their own radiation of heat back downward to the surface to just balance the heat that's going up, and that causes the atmosphere and the surface to remain warmer than they would be if the clouds are not there. And that's one of the things that can, at certain times, partially melt sea ice. So all of this is looking at clouds on a macrophysical level, but what if we zoom into a cloud and look at the individual cloud droplets and what happens to them over time? So this is a diagram of the different microphysical processes that occur in clouds over their lifetime. Microphysical meaning on the very smallest scales, on the size of individual cloud droplets. And individual cloud droplets in a cloud on Earth tend to be about a 10 millionths of a meter, let's say, in size. They're very tiny. And if you start in the lower left-hand corner of this diagram, you start out with some amount of water vapor or humidity in the air. And then you produce excess vapor going from the bottom left to the upper left, usually by lifting the air up so that it saturates. Now there's more water vapor in the air than the air can have without beginning to condense some of that water out. And so now moving from left to right in the upper panel, the excess vapor starts to turn into small cloud droplets just by more and more of the supersaturated vapor condensing onto the existing droplet after it forms. And then eventually, the droplets sometimes, not always, but sometimes grow big enough that they fall fast enough through the atmosphere that the turbulence in the atmosphere can no longer hold them up. And so they begin to fall out of the atmosphere, the larger cloud droplets, as precipitation. Sometimes that precipitation makes it to the ground. Sometimes the precipitation evaporates before it makes it to the ground. Regardless of which happens, the precipitating particles, as they descend, will start to evaporate once they fall below cloud base into the air that's no longer saturated. And eventually the big particles will form small particles, and eventually the small particles will evaporate completely, and you go back to the vapor phase. So that's kind of the entire life cycle of a cloud droplet. Now, moving back to the larger scale, to the planetary scale, why do we care about clouds? Well, most of you can probably figure out why we care about clouds when it comes to weather, because clouds are the things that produce rain and snow. But why do we care about clouds from a climate standpoint? Well, we care about it for those same reasons that we care about it in a weather sense. But what people probably don't think too much about in everyday encounters is how clouds affect the climate radiatively. And they do that in two different ways. They affect the climate by modulating how much sunlight the Earth absorbs, and that's because clouds are brighter than most everything else on the Earth. And so when sunlight comes in, when it encounters a cloud, the sunlight is likely to get reflected, and any sunlight that's reflected back out to space is no longer available to warm the Earth system. So that's one effect of clouds. The other effect of clouds is their greenhouse effect. And as I mentioned earlier, certain types of clouds are very effective at reducing the amount of thermal radiation or heat radiation that is emitted to space. And so if you reduce the amount of heat radiation that goes out to space, you're preventing the Earth from cooling off as efficiently as it would otherwise, and that's a warming effect or greenhouse effect on the atmosphere. And so scientists quantify those cooling and warming effects of clouds using a quantity that is typically called cloud forcing, sometimes it's called cloud effect, and it's defined as how much shortwave, and that shortwave means sunlight, is absorbed by the planet, or how much long wave or infrared, thermal infrared or heat radiation is emitted by the planet actually versus what it would do if the clouds are not there. And so the diagrams on the right show you then what role clouds play in different parts of the Earth. On the left, you see the role that they would play if there were no clouds in the atmosphere. And so if there were no clouds in the atmosphere, there would be lots of sunlight. Those are the bright lavender and purple colors. There would be lots of sunlight absorbed in the tropics, where the sun is most directly overhead the largest amount of the time, and less sunlight absorbed at the high latitudes, where the sunlight is most indirect. With clouds, on the right-hand side of the upper panel there, the effect of the clouds is actually to distort that simple picture in the places where clouds are most frequent and where they are thickest. And so you can see that there's a band of thick clouds that encircles the planet near the equator. We call that the intertropical convergence zone. And that causes those bright red areas, which means the clouds are reflecting a lot of sunlight and reducing the amount of sunlight that the planet can absorb. And you also see that in the mid-latitudes, all across the southern mid-latitudes there, and off the east coasts of the continents in the northern mid-latitudes in the storm tracks, you can see that the clouds reflect a lot of sunlight there. Those are the red areas on that diagram. In the bottom panels, you see the effect that the clouds have on the emitted thermal infrared or heat radiation. And the atmosphere without clouds on the lower left would emit most radiation to space, again in the tropics, because that's where the air is the warmest, and warm air emits more heat than cold air does, all things being equal. It's actually modulated a little bit by the fact that that more humid air emits less heat to space than drier air does. With clouds, though, again, the cloud systems modulate the effect, the greenhouse effect of the clouds, and in the areas that are green, the storm tracks, the intertropical convergence zone, you can see that the clouds are reducing the amount of heat that is emitted to space. And so in certain parts of the atmosphere, either the effect of clouds on absorbed sunlight or the effect of clouds on the heat emitted to space dominates. Overall, the effect of clouds on absorbed sunlight dominates. And so overall, we would say that the Earth is a cooler place, excuse me, because clouds are there than it would be if we had no clouds. All right, moving on to the next slide. One of the big questions for us is what's going to happen to the Earth as people put greenhouse gases like carbon dioxide into the atmosphere, as they add little aerosol particles into the atmosphere, and other things like that. And part of the answer is relatively simple. You put more carbon dioxide into the air and the planet warms up. But it turns out that that's really just the beginning of the story. And the rest of the story is that once the carbon dioxide begins to warm up the atmosphere, that sets into motion a chain reaction of processes going on throughout the atmosphere and on the Earth's surface that either amplify or mitigate the warming caused by the carbon dioxide itself. And clouds are an important but poorly understood component of that story, and it's one of the most active areas of research in Earth climate science today, is what role clouds will have to either amplify or decrease the warming due to additional greenhouse gases in the atmosphere. And that amplification or mitigation effect of clouds is called the cloud feedback on climate change. And one of the reasons it's so complicated is because there are many different types of cloud feedback that each play their own role. So perhaps the most important one, the one that most people would think about first, would be what's called the cloud cover feedback. There's a standard story that is out there in the world about what the cloud cover feedback is, and the story you usually hear in the newspaper is you warm up the Earth, the oceans warm up, the warm oceans evaporate more water into the atmosphere. Since there's more water vapor in the atmosphere, that makes more clouds. More clouds makes the Earth brighter. It reflects more sunlight, and that makes the Earth cooler. We would call that a negative feedback. It opposes the warming due to the carbon dioxide itself. Well, that story is just wrong. That's not what happens, because clouds do not depend on how much water vapor is in the atmosphere. They depend on the relative humidity, how close the air is to saturation. And when you warm up the atmosphere, you do put more water vapor in, but you also make the air warmer, which means that the relative humidity might not change at all. And so part of our job as climate scientists is to figure out whether in a warmer climate, we're actually going to have more clouds or fewer clouds. If we do have more clouds in a warmer climate, that will be a negative feedback. But most climate models predict actually that we'll have fewer clouds, which would be a positive feedback. And that depends mostly on the weather more than anything else. Another feedback is called the cloud height feedback. And that is a feedback by which, as the climate warms, the high clouds, the cirrus clouds in the atmosphere, especially the clouds that are produced by deep convective storms, tend to increase in altitude. They're at higher altitudes in a warmer climate than they are in a cooler climate, and that reduces the ability of the atmosphere to emit thermal radiation to space, and that increases the greenhouse effect of those clouds relative to what would happen if you did not have that change in altitude. And that's happening many, many kilometers above the Earth's surface. And so you may wonder, why do we care about it down here at the surface? The reason we care about it down here at the surface is that anything that happens high up in the troposphere is eventually communicated back down to the surface by the circulation of the atmosphere, by the convection of the atmosphere. And so if you warm things high up in the troposphere, eventually that shows up as warming at the surface. Another feedback is called the cloud optical depth feedback. That's a pretty easy one to understand, that if you condense more water in a warmer climate, then the clouds become brighter. And the question is, do you condense more water in a warmer climate? And scientists are still trying to figure that out. You can make clouds brighter either by putting more liquid water into them, by increasing their physical thickness, or by changing how big the cloud droplets inside the cloud are. And those are all contributing to whether the clouds get brighter or not. A related feedback is called the cloud phase feedback, and this is one that people don't usually think of. I mentioned earlier that we can make clouds out of either liquid droplets or ice crystals. And in some parts of the globe, especially at high latitudes, clouds sometimes exist as liquids, sometimes exist as ice, and sometimes exist as a combination of both. Well, if I go to a warmer climate, there's probably going to be more liquid droplets and fewer ice crystals. Why does that matter? It matters because liquid droplets, which are smaller, reflect more sunlight than larger ice crystals do, and that makes the cloud darker or less bright, and therefore, I'm sorry, that makes it brighter, excuse me, and that allows it to reflect more sunlight. That's important if you have a cloud that's over a dark ocean surface. If you have a cloud that's over a snow and ice surface, doesn't matter so much. And so again, scientists are trying to figure out how important is that cloud phase feedback. Then the last one, which is maybe the easiest one to understand, but the one that people don't think about much, is the cloud location feedback. You can take a cloud and not change the cloud at all. All you have to do is move it to a different location where the sunlight is different. And that will change the effect that the cloud has on the climate. The simplest example is take a cloud on the day side of the planet and move it to the night side of the planet. The same cloud that was reflecting a lot of sunlight at noon reflects no sunlight at midnight. And so therefore, that's a cloud feedback that's just caused by where the cloud is. And the same thing will be true if you move clouds from low latitudes to high latitudes, if you move clouds from over the dark open ocean to over bright sea ice. All of those things will affect the role that the cloud plays in climate, even though the cloud itself did not change at all. So this next slide shows you what the consensus among today's climate models is about what role clouds are actually going to play in climate change. And all this is a figure about the degree of consensus among the models. Consensus does not equal understanding. Cloud feedback is a very uncertain topic, and the hatched areas in these figures show you the places where the climate models tend to agree, and the places that are not hatched tell you the places where they tend to disagree. The bottom line from this diagram is that the majority of GCMs predict that as we go to a warmer climate, we're going to have fewer clouds, less cloud cover than we have now, especially in the tropics and in the mid-latitudes, what we call the extratropics. They predict that we're probably going to have more cloud cover up at high latitudes in the Arctic and the Antarctic. And they predict that there will be a shift from more ice to more liquid for the clouds in the Arctic and the Antarctic. That will be a negative optical thickness feedback because the clouds are getting brighter. We don't know yet which of those things are correct, if any of them. And that's what this next slide is about. Some features of predicted cloud feedback are considered high confidence. Doesn't mean they're right, it just means that we think they stand a good chance of being right. And so this feedback due to increasing cloud altitude with warming, a positive feedback, that is something that every climate model predicts without exception, and it is something that, to the extent possible, has been verified in satellite observations of changes in the current climate from year to year. And so it's one of the feedbacks we have the most confidence in. We think that it is due to a phenomenon called the fixed anvil temperature mechanism, which involves the altitude at which convective clouds dump moisture and ice into the atmosphere, following how the vertical profile of water vapor changes goes as the climate changes. That's considered a well-understood feedback. Another well-understood feedback is that the Hadley cell in the tropics seems to be expanding poleward. There's some evidence for that in observations as well. And we believe that by moving the storm clouds to higher latitudes with less insulation, that you will get a positive feedback from that. I would say that is not as certain as the positive long wave feedback above, but it's one that all the models produce to one extent or another, even though they disagree on the particular mechanism that causes it. Unfortunately, what's going to happen to low clouds in the tropics, which turns out to be perhaps the most important component of cloud feedback, is also the component of cloud feedback that the models disagree the most about. And this is why some models are what we call low sensitivity models, others are high sensitivity models. Some models actually predict that those clouds will increase as the climate warms, others predict that they will decrease as the climate warms. And this is the single most active area of research in cloud climate interactions in general. And until we can come to some agreement on what's actually happening and replicate that in our models, we're going to maintain the fairly large uncertainty in our estimates of the climate sensitivity of Earth in response to increases in greenhouse gases. There are other uncertainties. People don't really understand the cloud phase contribution to cloud feedback because it depends on really complex physics involving which particles ice crystals grow onto and how they grow. Thin cirrus clouds, which also contribute a greenhouse effect to the climate, are very thin and unresolved by the GCMs, the global climate models that are being used to predict their feedbacks. We don't understand very well how they're produced and how they're maintained. And finally, the optically thick anvil clouds that we see when big convective systems move through are produced by processes that are not represented in any climate model. And so the role that they're playing in climate model is still just debated. Finally, we have another uncertainty in cloud climate interactions, and that is how they interact with aerosol particles, okay? And so all clouds in the atmosphere have to condense onto some kind of particle. In our atmosphere, it tends to be something like sulfate droplets or carbon particles of different kinds. Under certain circumstances, you can get ice that will nucleate onto dust particles or biogenic particles that originate in the ocean or from vegetation on the Earth's surface over land. And once you think about that, then you can imagine that the number of aerosol particles available to act as seeds or nucleating sites for clouds to form on will make a difference in the properties of the clouds that occur. And so if I am in relatively quote unquote clean air with few aerosol particles, then the available water will condense onto a small number of particles and make fewer but larger droplets. Whereas if I'm in more polluted air, the water will condense onto a larger number of particles and make a larger number of smaller droplets. And the larger number of smaller droplets will reflect more sunlight than the smaller number of larger droplets. And so the aerosols will brighten the cloud. That's typically been called the first indirect effect, and that could cool the climate. There's another indirect effect that occurs when you think about what then happens to these smaller versus larger droplets once they do form. And people have suggested that smaller cloud droplets will precipitate less efficiently, and that will leave more water in the cloud to reflect more sunlight. We have no idea whether that process actually works in nature or not. It's very difficult to find observational evidence for it. There's another effect called the semi-direct effect, by which effects of aerosols on the atmosphere itself. So for example, if we have darker aerosols like black carbon or dust, they could heat the atmosphere locally and evaporate cloud droplets. They could affect the stability of the atmosphere and the meteorological processes that form clouds. Many different possible effects, and they're mainly very uncertain. And then finally, we have interactions between aerosols and precipitation. The most obvious one is called scavenging or wet deposition, whereby precipitating droplets, rain, collect aerosol particles and remove them or wash them out of the atmosphere below cloud base, or if they take particles inside the cloud that get carried with them when they rain out. This is the primary mechanism for removing aerosols from the atmosphere. It's a very important way of removing aerosols from the atmosphere. If we didn't wash aerosols out of the atmosphere, over time the Earth would become a very murky, hazy place. It would start to look a little bit more like Venus. And so it's a good thing that we have this wet deposition mechanism. There's another mechanism involving the invigoration of convection, whereby aerosols inside convective clouds, thunderstorm clouds, make it more likely that liquid droplets will be carried up into the colder reaches of the cloud and increase ice formation there. And that releases latent heat that strengthens the convection. That's a very controversial hypothesis, and we have no idea whether it works. Okay, so just to sum up, clouds form by two different mechanisms, either convective instability or because we lift stable air masses. In that sense, they're tracers of the Earth's general circulation. They transport, convective clouds transport heat and moisture and momentum. We didn't talk about that, but momentum too. And they produce much of the Earth's precipitation. Stratiform clouds don't do so much of that. They produce some precipitation, but they cover a much larger area and dominate the radiative effects of clouds on the climate. Clouds with low and high tops play different roles in the climate system via how much precipitation, rain or snow they form, and or whether they influence primarily short wave, and that's sunlight, or long wave, that's thermal infrared heat radiation. Cloud feedbacks as the climate changes are due to changes in cloud cover, cloud height, cloud optical thickness, cloud phase, and cloud location. Some of these feedbacks are well understood and others are not. And the ones that are not well understood are the things that primarily limit our ability to predict climate change. And then finally, the interactions of aerosols with clouds affect the cloud optical thickness or brightness and potentially the cloud cover and precipitation. And these are even more uncertain to a large extent than the regular cloud feedback mechanisms. Thanks for listening.
Terrific, thanks so much. We are going to turn it over to a Q&A period right now. So again, if you have any questions, if you either go to the top or the bottom of your screen, a pop-up should come up where there's a chat button, and you can submit your questions in there. We're gonna start off with a question and some discussion from David Rind while we give you guys a chance to type in any questions that you might have.
Tony, thanks. That was an amazing presentation, very clear from a very complicated subject. So my question, which is really almost a facetious question, is you've been in this business now for a number of years, and you've seen how our understanding of the role of clouds in climate has progressed. But as you said quite clearly, there's still a number of uncertainties that prevent us from having a full understanding of how the cloud changes will affect the climate system. Do you have any estimate as to how long it will be before we will have a good enough grasp of this to be able to estimate climate sensitivity with a much greater degree of confidence than we have now?
So I think there is a path forward on that problem, and the path forward, I think, involves primarily what we are beginning to learn from satellite observations. What has happened in the last few years is that scientists have become very interested in producing from observations what they call emergent constraints, which are behaviors of clouds that we can observe in satellite data for the current climate and how the clouds respond to changes in temperature or other things in the atmosphere, and which of those so-called emergent constraints are indicative of how we can expect clouds to respond in a climate change. This has become a cottage industry, actually, over the last decade, and there are now tens, about maybe 20 or 30 total, probably, of proposed emergent constraints in the atmosphere. The problem with those emergent constraints is which ones are reliable and which ones aren't. And the good news is that there are people who are starting to think about how you would decide which of those possible observational constraints are actually relevant to climate change and which are not particularly relevant to climate change. We're not there yet, but we're getting to the point where people are thinking about those things seriously. And I suspect that within 5 years or so, we are going to have probably some fairly reliable emergent constraints from observations that we can take as an answer external to the climate models about how certain types of clouds behave. So for example, I mentioned that the the feedback due to changes of low cumulus and stratocumulus clouds as the climate changes. That's a big uncertainty, the biggest uncertainty probably in most climate models. Well, before we fix that in climate models, observations might be able to tell us at least the sign of the right answer, if not the magnitude of the right answer. Once we know that, we will at the very least perhaps be able to tell the difference between climate models that are making a well-founded prediction and climate models that are not. And then once we do that, then we'll be able to start to categorize climate models according to which ones we think are more reliable predictors of future climate. What's going to take longer, I believe, is to fix the climate models so that we all agree on what the relevant mechanisms are and are all successful at producing the same types of predictions for reasons that we think are physically defensible. I think that's going to take a longer time. So I would say the first of those is going to take maybe 5 years. Second of those probably is going to take another decade at least.
Great. We have a question from a participant named Bernadette. She's asking if there are any suggested demonstrations or activities to help with the public understanding of cloud formation.
So I think there are certain things that you can do as a modeler. I don't think about observations very much compared to people who actually do the real thing. So you can obviously make clouds if you put humid air into a container and then let that container cool. The first thing that's probably going to happen is that you will see the water condense onto the surface of the container. That's not exactly the same thing as the actual clouds that form in the atmosphere, but it does illustrate that when you take humid air and make it cooler than water vapor, which you can't see with your eyes, humidity, you can't see it. It's an illustration that when you cool humid air, then it is more likely to turn into liquid water. Much harder to actually make real cloud droplets inside a chamber that the average person can use. There are many scientists who actually do experiments with clouds in laboratory setups where they actually produce cloud particles inside chambers, but those are under very controlled conditions where they're specifically trying to avoid having the water condense onto the walls of the container and things like that. But that's the only type of thing that I could imagine doing that would illustrate the formation of clouds. There are ways to, I think, in the real world, understand the radiative role of clouds. I think it's very easy to understand the effect of clouds on reflected sunlight, because we all know that on a cloudy day, or when a cloud passes overhead and blocks the sun, it gets a little bit cooler, and the hottest days that we get are usually the days where there are no clouds around, and once the cloud comes in, it gets cooler. What perhaps people think less about is the greenhouse effect of clouds, and perhaps the easiest way to notice that, if you're paying attention, is to take a cold winter night when, let's say at 7 o'clock in the evening, there are stratus clouds overhead, and over the course of the night, the clouds gradually dissipate, and you'll find that when the clouds dissipate, the weather will get colder. In fact, that's something that I think maybe goes into some weather forecasts, or that introduces uncertainty into weather forecasts of the coldest nights, when they're predicting that the temperature is going to go down to 0, and they don't really know whether it's only going to go down to -3 or +3, or whether it's going to actually get down to 0 or below 0. And part of that uncertainty is if the clouds do dissipate, it'll probably get a few degrees colder than if the clouds don't dissipate. And that maybe is one way for you to notice, at the surface at least, the role that clouds are playing in infrared radiation.
And then I think Matt just shared a link that could be a good resource for some teachers. So Matt, I'm going to unmute you and see if you can give us a little bit of an explanation for the link that you just shared with us. So go ahead and see if the sound works for you.
Hi, can you hear me now?
Yes.
Awesome. Hey everyone, not to interrupt the progress, but with the link I posted in the chat box is found on NASA's Wavelength site, and that's a online repository of a variety of different types of NASA education lessons. In short, this is a lesson plan that allows teachers and students to create a cloud in a bottle by following those specific instructions. So it's quick, and it's just requires a few materials of a 2-liter plastic bottle and some ice and other steps. But we've gotten a lot of great feedback about it and thought it might be relevant.
That's great. Thanks so much. We'll take one more question here. We just got one from Sylvia, and she says, how do you take the multi-scale nature of a cloud formation and effects into account as a researcher? Do you focus on just the micro or macro scale within a given project, or do you always try to consider the coupling of the two?
Yeah, that's a really hard problem to solve. So the way that we do it in science is, first of all, we have different kinds of models. Okay, there is no one size fits all in cloud science and climate science. We have models like GCM's global climate models that try to encompass the entire planet, and they do that at the cost of not being able to represent directly the very fine details of the clouds in any one location. And so GCMs divide the globe up into boxes, what we call grid boxes, that are, let's say, maybe on the order of 100 kilometers on a side or so. And they imagine that there are, we imagine that that there are many different clouds in that box, and we try to represent the collective effect of all of those much smaller individual clouds on the temperature and the humidity and so on of the air inside the larger grid box. We call that parameterization. So if I can give you an example of parameterization in the real world, consider microwave popcorn. It comes in a bag that's much bigger than any one individual kernel of popcorn, and the parameterization is stick this inside your microwave and turn it on high for 2 minutes or whatever. And when you take it out, you won't know which was the first kernel to pop or the second one to pop, but you know that if you follow those directions, most of the kernels in there will pop, and you don't care about the details of which one popped first or second, or whether it was one on the left side of the bag or the right side of the bag or whatever, right? And so that's kind of what parameterization is. It's saying, well, we know that there's going to be a lot of clouds popping inside the grid box, and we don't care exactly which one does what when. We just care about what the collective effect of many of those clouds is. So that's how a GCM deals with that question. But parameterizations, unlike microwave popcorn, well, even microwave popcorn directions are not totally reliable, because sometimes you'll open your bag of popcorn and find out that about 10% of the kernels aren't popped, and you're not too happy about that, perhaps, right? And in the same way, parameterizations don't always give you exactly the result that you like, and you may not be certain of what the right parameterization is. And so there are other kinds of models that we can run that don't try to simulate the whole globe. They try to simulate just one region of the globe, let's say the size of one individual storm system, and they simulate that at very high resolution with boxes that do try to represent each individual cloud, and they watch what happens in detail to those individual clouds. And so we try to use both kinds of models to get different kinds of insights, and we try to learn from the more limited area but fine scale models about some of the things we may be doing right or wrong in our big global models and use that to improve our representations of clouds in the global models. Maybe one of the more amazing things is that we're now at a point in computing power where you can now run a model of the entire globe at a scale where the boxes you can divide the atmosphere up into are getting to be close to the size of individual clouds. And so we're almost at the point where we can merge those two types of models into one gigantic model that doesn't have to parameterize a lot of the processes anymore. It still has to parameterize the microphysics, the individual parameterizations that say, how fast do the individual droplets inside the cloud grow, which clouds will precipitate, which ones won't, and so on. But it does get rid of a lot more of the macroscopic uncertainties that we have in things. The problem with those models is that they are very, very expensive to run, and so we can't use them yet to predict climate change. But a decade from now, maybe we'll be at that point.